All right. So we are coming down to it. This is lesson 33. There are only 42 lessons. So we are down to it. This is the final 10 countdown on our way to the end of Math 221 here at SUNY Geneseo. On today's show, the chain rule, but in reverse. And here's what I mean by that. Let's pretend that we're looking to find this indefinite integral. And we're thinking to ourselves, wait a second. The antiderivative of cosine involves sine. So maybe the antiderivative of cosine x squared has sine of x squared in it. How would we check ourselves? Well, the derivative of the sine of x squared, that's cosine of x squared times the derivative of x squared, so we know that we're okay. We know that we're okay. Similarly, we're thinking to ourselves, wait a minute. The weightiest function over here is sine of x squared. So maybe it's a 3 sine of x squared. So maybe, how would we check ourselves? Well, we'd take the derivative of something cubed, and the derivative of something cubed is 3 something squared, that's this part, times the derivative of what's inside parentheses. And so we know that we're right. Sometimes we can figure this stuff out just by inspection, just by looking at the integrand and reasoning through. But I'd kind of like to come up with something a little bit more, a little bit more generalizable. And so what we do here is what mathematicians call the substitution method. The substitution method. So we assume that there's some capital F that's an antiderivative of little f. Notice that this means that capital F is an antiderivative of little f. Then, if we have an integral, and the integral has little f, but it's not just little f, it's little f at some function. So it's not x squared, it's something squared. It's not the square root of x, it's the square root of something. It's not the sine of x, it's the sine of something. If the derivative of that inside piece is hanging out inside your integral, if the derivative of this inside piece is hanging out somewhere, then we just do capital F at u plus a constant. And as the side note here, la, did you turn your head? I hope so. We do this by expressing the integral of f of u of x, u prime of x dx as the integral of f of u du. That's the method to our madness. And because we usually are explicit with this u, this is often referred to as U-Substitution. That's how it's often referred. So let's evaluate the integral of 3x squared times the sine of x cubed dx. Let's find that integral using this process. And so we think to ourselves, this is a function of x whose derivative happens to be like right there. So maybe we let u be x cubed. I don't want to be x cubed. Well, that's fine. if u is x cubed, then the derivative of u is 3x squared, which means that the du piece is 3x squared dx. Remember what we're trying to do? We're trying to express things as an integral of f of u du. So what happens here? This integral is the integral of the sine of x cubed, but x cubed is u. And then this little line of mine replaces all of that. The 3x squared dx is just du. And you'll remember that this variable is a dummy variable, which means that it could be sine x dx, sine u du, sine t dt. It doesn't matter. We do those integrals in the same way. We think about the thing whose derivative is sine u, and then add a constant. That's what indefinite integrals are. We take the antiderivative, and then we take all of them. So what does that mean? Well, u is not part of the original problem, so we replace u with u. And we're done.
Sir, I'm going to feel a lot better if you do one more of those.
I figured that you might. I'll do 2 more of those. Let's do the integral of x times x squared plus 9 to the 5th dx. We can do this. We can do this. The trick here, you're imagining that this makes a good u, right? You're imagining that that makes a good u because its derivative is pretty much hanging out right here, but it's not. Like we want a 2x in that spot. How do we get a 2x in that spot? Well, we just sort of make it happen. But you can't just multiply by 2. That breaks all sorts of rules of math. But you can multiply by 2 if you also multiply by 1/2. And so that's the slick trick game we play here. We multiply by 1 in a creative way. We multiply by 2 to make this thing work out right, and then we compensate on the outside. So what is this? This is 1/2 integral of, the thing in parentheses is u, and then all of this other stuff, this 2x dx, all of the other stuff, well, that's really du. That's really du. And then we do this in exactly the way we would imagine doing this. We take an antiderivative of u to the 5th. Increase the power by 1, divide by that new power, and then we take all of the antiderivatives. They all differ by a constant. So this is 1/12 u to the 6th plus a constant. But the question didn't come to us in terms of u, so the answer can't come to us in terms of u. The answer comes to us in terms of u. And we're done. And I know that you wanted to see that one more time, and so we will. Let's ratchet up the level of difficulty. Oh boy. Oh boy. Well, by now you've done enough questions that you're thinking the thing in parentheses is probably u, and you're hopeful until you actually try to take the derivative. The derivative is not what we see up here. But it's close. It's close. And it would be spot on if we did this. But you can't just multiply by 3. That's crazy, breaks all sorts of rules. So instead, we multiply by 1 in a creative way. We multiply by the 3 up here and by the 1/3 out there. We have not changed the value of the integrand, and more importantly, all of this is a du. So this integral is 1/3 integral of 1 over u to the 4th du. Well, we don't know how to take antiderivatives of things like that, and so I'm just going to propose that we rewrite this. Because you do know how to take the antiderivative of something like this. You do know that you just add 1 to the power and divide by the power. And so now you're cooking with gas, right? Now you're totally cooking with gas. So this is -1/9 u to the -3 plus a constant. But we don't write u, we write u. We don't write u, we write u. Okay. We can also do substitutions with definite integrals. I will do that in a different video because we're at 12 minutes now. Okay, thank you.